Every once in a while, a story comes along that just feels like a classic David versus Goliath. And right now, believe it or not, one of the most exciting versions of that story is playing out in the world of artificial intelligence. Yeah, we're talking about a tiny, brand new AI model that's taking on the absolute biggest names in the industry, and it's winning. Okay, you're going to want to see this. So let me just ask you this right up front. Does this seem possible? Can an AI with, get this, less than 0.01% of the brainpower of a tech giant solve puzzles that the giant is completely stumped by? It sounds kind of crazy, right? Well, hang on, because as we're about to see, the answer is a huge, resounding yes. To even begin to understand how this is possible, we first have to wrap our heads around this really strange weakness that's hiding inside today's most powerful AIs. It's something we're calling the AI puzzle paradox. I mean, we've all seen what these large language models, LLMs, can do. It's amazing. They can write beautiful sonnets, they can spit out complex computer code, summarize an entire book in seconds. But here's the paradox. Give them what looks like a simple logic puzzle, something like a Sudoku, and they just fall apart. It's like all that creative genius just doesn't translate to structured step-by-step reasoning. And look at this. What's so wild here is just how completely they fail. This isn't about getting it right some of the time. On the set of really tough Sudoku puzzles, some of the most powerful AI models on the planet, we're talking models with hundreds of billions of parameters, have an accuracy of zero, a flat zero. They literally can't do it. And that's the problem that really demanded a whole new way of thinking. So researchers knew they had to find a different approach. And that brings us to the first major attempt to solve this puzzle paradox. A really clever, but as you'll see, an ultimately super complicated new type of model. This first crack at the problem was called the hierarchical reasoning model, or HRM, and the core idea was pretty cool, actually. It tried to mimic the brain by using two separate networks that work together. One would handle the nitty-gritty details, kind of buzzing along at a high frequency, while the other took care of the big picture at a lower frequency. It's a fascinating idea for sure, but it came with a lot of baggage. Yeah, and this quote from the original paper kind of says it all. The whole justification for why HRM should work was based on these really complicated theories about biology and some advanced math, these things called fixed point theorems that, well, might not even apply in the first place. The whole foundation was just a little shaky. So, to just boil it all down, while HRM was a really interesting step, it had some serious problems. It was built on these uncertain biological ideas, its math was questionable, it was a pain to train, and at the end of the day, it was just too complex with its two separate networks trying to work together. This whole situation was just begging for a breakthrough. And that brings us to the hero of our story, a new model that took the core concepts from HRM, but then just stripped away all the complexity and ended up creating something way, way more powerful. Meet the tiny recursive model. Okay, take a good look at this slide because this diagram is the key to everything. This is the tiny recursive model, or TRM. And right away you can see, instead of two networks, there's just one. So it takes three things as its input: the question, a first guess at the answer, and its own internal reasoning. It feeds all three of those into that single network, which then thinks for a second and updates the reasoning. Then, and this is the magic part, it uses that new, smarter reasoning to update the answer. You could almost think of it like an artist sketching, right? They draw a line, they step back, look at it, think, not quite, and then they erase it and draw a better line. TRM does that over and over again, up to 16 times, just refining its own work until it nails the solution. And that right there is the beautiful paradox at the heart of all this. By making the model radically simpler, the researchers actually made it dramatically better. It's a perfect example of less is more in action. So why? Why does making it simpler work so well? Let's break down the specific design choices that let this tiny AI just completely dominate where the others fail. This chart just makes it crystal clear. You've got HRM, the old way, with its two networks, its complicated justifications, and its inefficient training process. Then you have TRM, the new way, a single tiny network, a super simple and intuitive loop of just improving its answer and reasoning. It's way more efficient to train, and it gets rid of all that shaky math. It's just a cleaner, smarter, more elegant design, period. So let's just walk through that process one more time, because this is the absolute secret sauce. It's this simple, powerful loop. You start with a question, a guess, and some reasoning. You use all three to think a little better. You use that better thinking to come up with a better answer, and then You just do it all over again. This constant refinement is TRM's secret weapon. And here it is. This is the big philosophical shift in how we should think about building AI. For years, the main approach has been to just build these massive, massive networks, hoping that their sheer size will let them get the answer right on the first try. TRM proves that for some really hard problems, it's way more effective to build a tiny network and just give it the ability to think again, to check its own work and make it better. Okay, so a clever design is one thing, but does it actually work in the real world? Let's look at the numbers, because this, my friends, is where the story gets really, really good. And the results are just wow. They're stunning. On that same super hard Sudoku test where the giant LLM scored a big fat 0, the original HRM model got a pretty respectable 55% right. But TRM, the simpler, smaller model, it just blows it out of the water with over 87% accuracy. That is a massive leap in performance from a much smaller model. Now, how small are we talking when we say tiny? The winning TRM model has just 7 million parameters. Let that number sink in for a second. In an era where we talk about models with billions of parameters, 7 million is absolutely microscopic. And just for contrast, remember that DeepSeek R1 model we saw earlier, the one that scored 0 on the Sudoku task? It has 671 times billion parameters. That means our little TRM is beating a model that is nearly 100,000 times its size. This is the definition of David versus Goliath. It's insane. And this wasn't some lucky fluke. Just look at the performance across these other notoriously difficult AI tests. On hard mazes and 2 different abstract reasoning challenges, the tiny 7 million parameter TRM consistently beats the larger, more complex HRM model every single time. The pattern here is unmistakable. Simpler and smaller is winning. So the big takeaway here is a really, really important lesson for the future of AI. For years, the mantra has been, scale is all you need. Just throw more data at it, build a bigger model. This research proves that for some of AI's toughest challenges, the real solution isn't brute force. It might just be a more clever, more efficient, and frankly, a more elegant algorithm. And that leaves us with this fascinating final question to chew on. We've seen that a better idea can crush brute force when it comes to logic puzzles. So, what's next? What other massive challenges in science or medicine or technology are just sitting there, waiting for a similar breakthrough? Not for more computing power, but from a smarter, more elegant idea. It really seems like the next big thing in AI might just be something very, very small.